Yeah, thanks for this opportunity. And yeah, I opened the next window to show some animation that I made, but I don't know. You guys are familiar with edit distance by now, but still I made this. uh, yeah, so you have two strings x and y, and the edit distance is the minimum number of operations you do. And I have this example from last year. Uh, so here it goes. So there is substitution first, and then another substitution. Just yeah, and then yeah, you can see the operations. I do not need to narrate. Right. So there will be 7 operations. Yeah, but I like this example. It was relevant for the venue last year. Right.
Let the arrow go.
Yes. Okay. Now, thanks. Yeah. Now we can start the talk. Yeah. So this is a joint work with my supervisor, Mikhail Kulsky. So the main technical contribution of this paper is this string decomposition, and we have shown the application that we can use this to construct edit distance sketches. Okay, so let me first start with the definition of sketching, and then I will go to decomposition, and then again back to sketching, and then finally the technical part. So this you do not need to know. So what is sketch? So given a string x, you construct a smaller object which is a sketch of x, and similarly you do the same for y. And you need to, so from the sketches of x and y, you have to compute the edit distance of x and y. So maybe for some of the applications you also need to recover the positions where there are edit operations. So this is the goal, and our target will be to make the sketch sizes as small as possible. So there is another catch, which is like while computing the sketch of x, you do not have the information of y, and vice versa. Otherwise, you can just say that I'll just compute beforehand, and that will be my sketch. Okay, so this is the definition. What is already known for exact edit distance sketches, given some threshold on the edit distance, which is the k. Belajongi and Zhang in 2016, they first showed that you can get sketches of size O tilde k to the power 8. Here tilde hides some polynomial factors. And they used the technique of...
Oh, maybe you have to unmute.
Yeah.
From my computer?
They all do in the
I thought this was...
bottom left.
No.
I think from this one.
No, make it first.
Am I audible now? Is it fine now?
Let's.
Perfect.
Yeah.
Oh, great. Yeah, so this was the first surprising result on sketches, and they used the technique of CGK embedding that Elazar already presented. It was a really nice presentation. And there were follow-up works on this, and they all used the CGK embedding. And the best known till 2021 was O tilde k square. So in last year, what we did is still O tilde k square size, but our sketch, our sketch uses a different technique, which is the locally consistent parsing technique. And the advantage of this is that we can use this for designing rolling sketches. So by rolling sketches, I mean you have the sketch for a string, you add some symbol at the end of the string. You do not need to construct the sketch from scratch. So you construct the sketch on the go as the symbols appear. So this is one advantage, main advantage, and also this is a new technique. Yeah. So the previous results, it was it was kind of a bottleneck for not having rolling sketches. Okay, so let me go back to the string decomposition. By string, what do I mean by the string decomposition, and what kind of property I want from this decomposition so that the sketches can be constructed. So I'll first say what properties I want. So suppose I have x and y, and these highlighted positions are the edit operations. And so these edges, you can think of this as a non-crossing matching between characters which are either matched or substituted. And this is called an alignment of x and y. So given this x and y, I want to partition the strings x and y into blocks, as this is a decomposition. And I want the following properties. That the first property is that the number of blocks in x and y should be same. And I want another property which is like, just pay attention to the next slide. So you see one block is now shifted. So now what is going wrong here is that one of the is the, yeah, it's visible. So one of the edges, it is going from a block to not its corresponding block but to some other block. So we do not want this property. We want that all the edges go from one block to its corresponding block. So given this property and the first one, it immediately implies the second property, because I am given that the edit distance of x and y is less than equal to k. And given, so this property and all the rest implies that now what I can do is I can compute the edit distance of these pairs and then sum them up to get my whole edit distance. So yeah, this kind, I want these, but this can even be achieved if I take a single partition, like x as a single block and y as a single block, right? So I need some property on the size of the blocks. So yeah, so the last property is that the block sizes should be small. So by size I mean the size in which the block will be represented. That should be small. Yeah, and all these properties should hold with high probability. Okay, so if this happens, then I call my decomposition as well aligned. Okay, so given the well aligned decomposition, now how do we get our sketch? So we again have x and y and imagine some alignment, and we start with the good well aligned decomposition. So the first property was that every block of x is perfectly aligned with a block of y. And there are some blocks which contain some edit operation. So is it visible, the difference of color?
Yeah.
Okay. Yeah, so these red kind of blocks are the ones that contain some edit operations. And our goal will be to recover these blocks completely. And yeah, so if we can recover these blocks completely, then we can just compute the edit distance of these blocks and sum them up. That was the, yeah.
So the decomposition is done independently?
Oh, yeah, that's a good point. Yeah, so that at the starting I said that when computing the sketch of X, you do not have information of Y. So yeah, I don't know if the picture is misleading, but the decomposition is done independently on X and Y. Okay? And yeah. So yeah, so you have these problematic blocks, and now what we do is we encode we encode the blocks in such a way so that if the blocks match, then the encoded blocks also match completely. And if there is some edit operation, if the block is problematic, then all the positions of the encoded block will differ. So the Hamming distance will be the length of the block, length of the encoded block. So just trust me, we can do this. So if we can do this, then we can use some well-known Hamming sketches to recover all the positions which have some which do not match. So there are linear size Hamming sketches which allow us to do that, linear in the number of Hamming operations. So here the number of Hamming operations is the number of problematic blocks, as we saw from the property of well alignment, is at most k, and we also saw that the size of the blocks is bounded is O tilde k. So the number of Hamming errors that we will get is O tilde k square here. So we can use O tilde k square size Hamming sketch to recover those blocks. Once we recover the blocks, we can compute the edit distance of the blocks. And yeah, so this is how we construct our sketch. And yeah, right. Okay, so now I'll move to the decomposition, like how do we do our decomposition. And I will start with the decomposition of random strings first. So here X is suppose the strings are binary and X is a random string. That means for every position you flip a coin. And Y is some string which has edit distance k from X. And again you have these alignment and the edit operations. These are just for the illustrative purposes. You don't have them. It's just for the illustration. So for random strings, what we can do, we can take a window, sliding window of size let's say log n, and we can hash the window to one of the 1000k log n buckets. And once we see that the hash function gives us 1, so the window is hashed to bucket 1, we start a block or end the previous block. So we do this, and one thing we have to be careful about is that there might be a case where the window is going through some edit places and still it is hashed to 1. So these are the bad instances that we don't want. So yeah, I will mark it as red, and we will show that this happens with very small probability. Okay, let me do this. So we did this for X, and independently for Y also we will do this. Okay, so now we will show that this, you can see that because of that problematic window going over the edit place, the number of blocks is now different. So we don't want the red one. So yeah, so what is the probability that any window will be hashed to 1? So one window will be hashed to 1. So it's 1 over the number of buckets, right? So and how many problematic windows can we have at max? So imagine one edit operation, and you're sliding the window through it. So how many windows will contain that edit operation? It's the length of the window, right? So it's log n. And so there are k edit operations, so at most k log n. Well, if you consider for both x and y, it's 2k log n. Yeah, so by union bound, you have that the probability of any problematic window getting hashed to 1 is small. So we don't have this red condition, and with high probability, so we are good to go. Okay, so far we did not use any property that the property that X is random. So if this happens for any string. Yeah, so we showed that the number of blocks in X and Y are same if that condition doesn't happen. And now we will use the fact that X is random. So X is random, that means the expected length of a block will be equal to the number of buckets, right? But Y is not random, but this also happens for Y. Because in Y, how many more symbols or less, how many more symbols can we have? We can have at most k more symbols, so the size is still O tilde k. So yeah, so with high probability, we actually have all the properties of the well alignment for random strings. Okay. So what will not work for non-random strings? So remember, with high probability, none of the problematic windows will be hashed to 1. This property will still hold for non-random string. The one that will not hold is that the expected length is bounded, because it might be the case that so here you can see there are repetitions of zeros, and the window will slide through and it will not break till a long time. So there might be many repetitions. So that is the problem. So what we can do is, if this happens, that means that we have a lot of repetitions, either of the same character or some pattern. So we will try to compress it. So that's the plan. So we use two kinds of compression.
5 minutes.
Okay. Yeah, okay. So we will use these two kinds of compression, which is compressing repetitive characters to 1, which is this rule, can be represented by that rule. But this does not guarantee us that we will compress every time, right? Because it might not happen that we get repetitive characters like 0 to the power something. So we also want to use some rule which takes 2 symbols and compress it to 1. Yeah, and there is there is one catch, that this pairing, it might be a problem. Why? Because this pairing might not be consistent. We can see that in the above example, we have 1, 0 getting mapped to 3, and here we are choosing to pair 0, 1. So even though x and y are same, the compression is not same. So we want some kind of consistent pairing, and yeah. So for this consistent pairing, we use this locally consistent parsing technique, and this has been studied for since long time, and it basically pairs the characters in a consistent way. I don't have time to show how, but just trust me that it pairs. We have the consistency property if we use this, and also we have the property that the compression will be by a factor of 2/3. So if we have like, so this is good, right? So we know that we are compressing to something. So yeah, so that's a good thing by a constant factor. So now the main idea is that we start with an initial split by the sliding window that we did, and now some of the blocks are large. So for those blocks we compress, and now we repeat this. So we split and then we compress, then we again split, and if some of the if the blocks are large, we compress. So we do this until we have all the blocks of size less than or equal to 2 characters. So the number of rounds, since every time we are compressing by a constant factor, is order log n. And we can show that, so we use these grammar rules, right? So we can show that in each of these levels, the number of distinct pairing is kind of bounded by O tilde k, because of the way we are hashing. I'm like rushing it through, but just trust me. We had this property that the number of problematic blocks is it is written bounded by k. Okay, it's bounded by, it's less than equal to k. No. So now, yeah. So right. So now we have that the total size of the sketch is O tilde k square. So yeah, this was it, and I had some open problems. These are very immediate open problems. I think Michal and Mike Sachs, they have an improvement over this, which is almost linear, and is going to appear this year in stock. So now it's linear in K is still open, and yeah. So I think your result doesn't do rolling, right? No. Okay. Yeah. So the rolling part is open. And yeah, here we did not analyze it very well, so maybe running time for the construction can be improved. Yeah, thanks.